All right, well, thank you for coming to my presentation today. My name is William Van Leeuwen. I usually go by Bill, and today I'm doing my presentation on FreeRTOS. Good motto for this is nothing's better than free. So your first question probably is, what is FreeRTOS? FreeRTOS, which stands for Real-Time Operating System, is a class of RTOS that is designed to be small enough to run a microcontroller. A microcontroller is a computer like this. We'll talk about that later. So, now you're probably wondering, what is a real-time operating system? A real-time computer system can be defined as a system that performs its functions and responds to external asynchronous events within a specified amount of time. Now I have a good example here. This is a nuclear reactor pictured. Now, if you don't know, a nuclear reactor works by having radioactive material in a reactor. The reactor will then cause there to be nuclear reactions. These reactions will create heat. These uranium rods get super hot. They will then heat up water, which heats it to its boiling point, which will then create steam, which then spins a turbine, which creates electricity. Now, the heat coming from these rods needs to be monitored. It needs to be controlled. If you let these reactions go out of hand, these can get up to thousands of degrees, hot enough to melt through the concrete below them and cause massive damage. Think of stuff like Fukushima, not quite Chernobyl, but Chernobyl is a good example. And the way that we cool these systems is with a computer. The computer will monitor the temperature and monitor button pushes to cool the reactor with water. It will pump more water onto the reactor as it needs. Now, say a nuclear scientist pushes a button. He or she or they want water on the reactor. This system needs to respond to that and accordingly, in a specified amount of time, put water onto that reactor. If it doesn't, like I said, it could melt down. Bad stuff could happen. So how does an RTOS, like FreeRTOS, differ from a regular operating system like Windows? Why don't we have Windows running on nuclear reactor cooling computers? So the main difference is the scope of their work. I have two computers side by side here. This one's my personal desktop. I'm running, like I have here, I have 24 Chrome tabs. I'm running Spotify, Discord, taking in keyboard and mouse input. I'm doing a lot of things. I'm actually working on my presentation. I have pretty hefty specs to be able to do this, and I could actually do much more if I really wanted to. And this is the kind of environment where something like Windows shines. Whereas on a computer like this, there is no way you could run this kind of stuff on there. This is an ESP32. It's sold by Adafruit. There are a lot of different configurations of this board. It's a pretty common microcontroller. It has 240 megahertz CPU, 520 kilobytes of RAM versus gigabytes. And that's fine though. That's kind of the whole point of these microcontrollers. They're very small, they're very cheap, and they can run what you need it to do. All it really usually runs is some C code. You're often taking an input from sensors, doing simple I/O operations, running LEDs. We're not going to get into exactly all the kind of things you can do with a microcontroller, but this is where FreeRTOS shines. Now it says here, the RTOS kernel itself only requires 5 to 10 kilobytes of ROM space, which is storage. And the scheduler only requires 236 bytes of RAM. Very tiny. The other difference in spot where you would use FreeRTOS is in a hard real-time system. I have this visualization here of the different kinds of systems. You have value and usefulness on the y-axis and the deadline pasted here on this bar. So a soft real-time system can be something like Spotify, like a music streamer. It responds to music data being sent over the network, and the computer then, the Spotify application, then interprets that and sends it out to your headphones. It responds to the asynchronous event of the music being streamed to the computer and then sends it out. If you miss the deadline on that, let's say the Spotify or the operating system misses the deadline, likely what happens is the music will stutter. It's probably happened to you actually. Even when you have like a YouTube video buffering, that's kind of what's happening. It's missing the deadline. And if it misses the deadline, it still has some value for some time. Like, you're not going to throw away your computer just because your Spotify buffered one time. Whereas you have on the exact other side of the spectrum, you have the nuclear reactor, what we were talking about. If the computer system that controls the temperature does not effectively control the temperature, it is garbage. It is not useless whatsoever. People will die if this computer doesn't do what it needs to do. And these are the kind of systems where FreeRTOS shines the best. So I want to talk to you about some scheduling. Scheduling is the job of scheduling jobs. And FreeRTOS has some pretty cool scheduling configurations. This is a simple diagram of the task states that FreeRTOS has. Very simple. If you're familiar with operating systems, you've likely seen something like this before. It has the API calls here, which will suspend tasks, get tasks ready, etc, etc. The main two that you need to worry about are the ready and the running states. The scheduler itself, its entire job is this section here. It determines what can be in the running state and what is in the ready state. My favorite thing about FreeRTOS is the ease of configuration of the scheduler. I downloaded the FreeRTOS source code, and look in this FreeRTOS config file. It just has these define statements here, which you can change of your own will and change the way the OS works. And in terms of the scheduler, you have here the preemption and the max priorities. You can actually turn preemption off and on just by typing a 0 or a 1 in this position. Now, it's not listed because it's by default active, and you really don't often need to change it, but you can also turn off time slicing. This can be useful for some applications. I don't exactly know where. I just think it's really cool you can change it. You can even change the number of priorities. If you want to have 10 priority levels instead of 5, 6 priority levels, 100 priority levels, you can do whatever you want. So we're going to go through the three kinds of scheduling you can do with FreeRTOS, configuring it yourself by changing these two options. The first is the default option, preemptive with time slicing. Pretty standard. If you've seen a diagram like this before, you probably already understand what's happening. Tasks get preempted by their priority levels, and tasks also get shared. That is preemption and time slicing respectively. See example here of time slicing with this idle task and task 3. Task 3 doesn't get blocked here. It just, the scheduler decides, okay, you've had your little section of time, you've had your one-time unit, now I'm going to give the one-time unit to time 5. And then we switch back to task 3, where it preempts, and it switches, it time switches. And then task 2 comes along, it preempts task 3. This is a pretty good example of time slicing and preemption, the default set. Now, let's say you don't want time slicing. You set it in the scheduler, and this is what you'll get. You have this idle task here that's running. You have two idle tasks. Task 1 leaves the block state and preempts the idle task. Task 1 re-enters the block state, which then task 2 starts running. So this kind of setup still allows tasks to cut others off, kick them out of the running state, but it will let other tasks run until they're finished. It won't share time. You don't see these two tasks sharing time between each other. And that can be useful for a variety of things. You also have the least default, non-preemptive with no time slicing, otherwise known as cooperative scheduling. So you see here, this very low priority task is running. Task 2 comes in. In a preemptive system, task 2 would start running immediately. It would preempt task 3. However, we have that turned off. So it waits, and along that time, task 1 unblocks. Once this task finishes, yields, which you need in this system, you need your tasks to stop or no other tasks will ever run. Task 1 starts. It still has priority-based scheduling. It doesn't run 2 because 2 came in first. It runs 1, but you're not preempting other tasks. So next we're going to talk about how FreeRTOS deals with concurrency. So it's pretty simple. We don't even really need to go into this too much, but it has two ways of dealing with concurrency: binary semaphores and counting semaphores. Pretty standard. We're not going to go into what each of those are. If you know what a semaphore is, then you're good. If you don't, look it up. So the interesting way that FreeRTOS can use binary semaphores and counting semaphores, if it really wanted to, is with interrupt service routines, ISR. The way that this is cool is that, let's say you have a task running. You want a second task to run upon an event. Let's say a button is pushed. You want something to happen. Task 1 gets an interrupt sent. The interrupt service routine then sets a semaphore. This task has been waiting for that semaphore. It's been blocked on it, and this task will have a higher priority than this task. So as soon as the interrupt service routine finishes, task 2 goes in. Once it finishes, it sets the semaphore back, and then task 1 is allowed to keep running. This is one of the super cool things you can do with the binary semaphore in FreeRTOS. And this is a similar diagram. It's the same exact process, but with a counting semaphore. It's the exact same thing. The diagram starts, semaphore count is 0. Think of this task as task 2. It's waiting. It's in the ready state. It's waiting for the semaphore. Once the interrupt happens, the semaphore goes up. The count goes up. The task is ready. It unblocks the task. The task processes the event. The interrupt keeps happening. Maybe you're pressing the button multiple times, you're pressing different buttons, and the semaphore count goes up to 2. The task can then run a specified amount of times. You can kind of use this as a cue to manage the concurrency and allow certain processes to run when you want them to. And that's really all there is to talk about FreeRTOS today. If you want to learn more, there's a pretty cool website here. It's just the FreeRTOS website. There's lots of documentation, lots of help, and most of the information I got for this presentation was from this book, the Mastering the FreeRTOS Kernel. It's a couple hundred pages long. If you really love FreeRTOS, I encourage you to read it. Otherwise, I appreciate you coming and watching my presentation, and have a good day.